are back to the second session of the day. Our first speaker is Junji Iwahara, and I'm very happy to have also somebody bringing the experience of the experimentalist to our community. Go ahead.
Thank you. Yeah, first of all, I would like to thank Walter and other organizers for organizing this wonderful meeting. We have both experimentalists and theoretical people. That's a really wonderful opportunity for us to share our experimental findings. As I said, I'm working on, I'm an experimentalist actually, and we are using NMR spectroscopy for our research on biomolecular electrostatics. Maybe here, the majority of the people are theoretical people, and experimental people are a small minority. But I would like to convince you that experiments can do a lot in biomolecular electrostatics. Okay. Conventionally, people study protein electrostatics based on structures, three-dimensional structures. You can calculate electrostatic potentials in three-dimensional space using PDB structures. And you can get something like this just from the structures. For such kind of calculations, you have to use a particular theory. But there are some possible problems about theoretical calculations. Here, I listed some of those programs. For example, if you use a Poisson-Boltzmann theory, the calculated electrostatic potentials may not be accurate near the first layer of hydration. And it may not be accurate at very high ionic strength. And for this kind of calculations, you need charges, but due to limitation in PK prediction, maybe charges are not really accurate. Another layer of complexity arises from conformational flexibility. Side chains are typically quite flexible, and loops of the proteins are conformationally quite flexible. And there are many kinds of proteins that doesn't have any folded domains. And such conformational flexibility makes the analysis of protein electrostatics very complex. So from the perspective of experimentalists, it would be really great if we could directly measure electrostatic potentials without using any structural information. That's what we are doing right now using NMR spectroscopy. And for that, I introduce you our new concept, which we call phi-ENS. It is effective near-surface electrostatic potentials, and this one represents an average of electrostatic potentials near the observed nucleus, and we can measure average electrostatic potentials in an exterior space for each observed protons in NMR experiments. That's what I'm going to demonstrate today. Of course, you wonder probably how such a measurement is possible, right? The principle of our method is so-called paramagnetic relaxation enhancement. Okay, in this experiment, we basically observe NMR signals from biomolecules, macromolecules, but we also use unlabeled materials shown here. They are small molecules with charge is either positive charge or negative charge, and it has an unpaired electron that causes PRE, paramagnetic relaxation enhancement. And through the experiments, we can measure paramagnetic relaxation rates, gamma 2, for the sample containing this small molecule, or for the sample containing this small molecule. And just from those two PRE rates, we can determine this effective near surface electrostatic potentials. Okay, this is a really simple equation, and you might wonder why such a simple equation can give effective near surface potential. I explain why it is the case. Okay, the most important equation here is the equation for the PRE arising from co-solute molecules. And this is basically showing how distribution of the paramagnetic co-solute molecules affect paramagnetic relaxation enhancement. And this U is the potential mean force. And if you convert this equation into a three-dimensional lattice space, the equation becomes like this. And this exponential term is basically just a Boltzmann factor. And from this, basically, we can any NMR specific coefficients just by taking ratio and retain geometrical or electrostatic factors in the ratio. And if the electrostatic potentials are near uniform in a particular small space, we can even cancel the distance term. And assuming that these two compounds are structurally very similar, and the only difference in the potential is electrostatic, we can basically get an approximation that this ratio is just this single exponential term containing phi ENS, near surface electrostatic potential. And from this, we get the definition of our effective near surface electrostatic potential phi ENS. All right. By experiment, we measure the PRE rates just using three samples. Okay, one sample is the solution sample of protein or DNA or any other biomolecules. And the second sample contains the small molecules with a charged moiety and unpaired electron. And they are diffusing around the macromolecules, but the distribution, spatial distribution is not uniform because of the electrostatic interactions. And we measure PRE rates for this co-solute molecule and this co-solute molecule separately. And here, this is an example of PRE rates measured for ubiquitin. Okay, for each residue, we can measure these PRE rates. And this is for backbone amide groups. Okay, using these PRE rates, together with this simple equation, you can calculate phi NS potential. Here, there is absolutely no fitting at all. So there is no adjustable parameters here, and we get electrostatic potential here. And probably many theoretical people here wonder how good these experimental data are. Right? I'm going to show it in a few minutes. Before I show it, I should explain how we can compare our experimental data with theoretical predictions. Okay, so this is the definition of phi ENS potential, and you can actually convert this one into a Poisson-Boltzmann version of the equation. And here, basically the PRE rates were converted into this, which can be calculated using electrostatic potentials from Poisson-Boltzmann calculation for each grid point, and also the grid nucleus distance for each grid point. And this summation is for the entire three-dimensional space. Okay, this is one way to back calculate phi ENS from the structure. The another way is to calculate simply just average for the near space of the, around the observed nucleus. And for that, empirically, if we use this criterion for the effective range, basically the calculation using the entire three-dimensional space and calculation using just local space become almost the same. I'm going to show it. Okay, so to give you an idea about this back calculation, here I show an example for ubiquitin. Okay, so this is ubiquitin structure, and these are effective near surface zone for just two backbone amide groups. One is for leucine 71, and the other one is threonine 22. And basically, our PRE data are affected by the co-solute molecules present within this zone. Okay, and this is basically just two-dimensional plot of the electrostatic potentials for the exterior region. And just by comparing these two on the same plane, you can actually see what kind of electrostatic potentials you can expect, right? But of course, you can also use entire grid space to back calculate the PRE, phi ENS potential. And this is just a three-dimensional representation of the same thing, and basically, by NMR experiment, we can get the near-surface electrostatic potentials from PRE data, and we can back calculate the phi ENS potentials from three-dimensional structure. Okay, here is the comparison of the experimental data with theoretical prediction. Okay, so red is what I have already shown. It's experimental phi ENS potential. And blue is the prediction from the, all the grid points together with electrostatic potentials. And green is calculation for the local space. As you can see here, the agreement between experimental data and computational predictions are pretty good. And if you do correlation plot, it's like this. Okay, so this is quite nice agreement. And when we saw it for the first time, we were really amazed because we didn't expect this kind of good agreement because of the crude nature of the simple equation we are using for phi ENS. Okay, but there are some discrepancy. For example, if you look at the C-terminal region, the predicted values and experimental values are quite different. And we thought that this could be due to structural flexibility, because some regions, like the C-terminal tail, could be structurally flexible, and that could affect the ensemble average. So we did same calculations for 100 structures generated from the original PDB structure. And it looks like some differences between experimental data and computational data are indeed related to structural flexibility. But that's not really the only explanation. And actually, One of the discrepancy, one of the factors that cause discrepancy is basically simplicity of the equation. We have actually published a paper on better approach for the back calculation. But anyway, experiment data and theoretical predictions are quite in good agreement for this one. Okay, we can measure phi ENS for other types of nuclei, like methyl proton or H alpha proton. And in any case, we got equally a good agreement with theoretical predictions. Yeah, we did this experiment for DNA as well. And DNA also gave quite a nice agreement, as shown here. We also applied this method to protein DNA complex. And here, the protein we used is highly positively charged. But when we measured the electrostatic potentials for the protein bound to DNA, the electrostatic potentials around the protein was all negative, as shown here. It's because DNA is strongly negatively charged, and there is a basically long-range effect even for the protein surface. Okay, we can use this methodology for something like IDPs or IDRs, intrinsically disordered proteins or regions. And we tested the method for HMGB1 DE repeats. DE repeats are quite common in DNA binding proteins. This is really strange set of sequence with just E and D, right? Yeah, many DNA binding proteins have this kind of sequence, and we measured electrostatic potentials for these regions. And here is the data. Okay. By the way, NMR analysis of this peptide was really challenging, although the size is relatively small, simply because the NMR signals are really in a narrow region. It's not surprising, right? Because there are only E and D here. But we were able to assign all the signals, and we measured the electrostatic potentials. And here is the measured near surface electrostatic potentials. One thing that was surprising was that actually this potential is even larger negative compared to DNA surface potential. Prior to this work, we measured surface potential using the same method for 15 base pair DNA, and it has almost the same charge, but still the surface charge was actually stronger, not charge, sorry, surface electrostatic potential was larger negative for this peptide. Sorry, do you have a question? Yes. Oh, that's a great question. Yeah, actually, there are slight perturbation when we added aminomethyl proxyl, which is positively charged, but that perturbation is quite small compared to what we typically see for example, protein drug complexes. So it's not really kind of strong binding. It is just electrostatic effect. But there were some perturbations. Okay. This is just for the isolated peptide, but we also did the experiment for the full-length HMGB1 protein containing this IDR. And this is the data for the full-length HMGB1. And we also measured phi NS potentials for the truncated protein that doesn't have the D repeat. And as you can see here, the phi NS potentials were clearly different. And that's because the D repeats interact with positively charged DNA binding domains A box and B box. Actually, such intramolecular interactions cause autoinhibition of the protein. Um, and affinities of the full-length HMGB1 is weaker compared to the truncated HMGB1. We can also see electrostatic interactions between the positively charged HMGB1 and negatively charged D repeats through simple chemical shift analysis. For example, here, if you look at the data at 700 millimolar KCl, the signals from A box and B box were pretty much the same for the full-length HMGB1 and the truncated HMGB1, but at lower salt concentration, like physiological ionic strength, the signals were quite different for these protein constructs due to the presence of electrostatic interactions between D repeat and the DNA binding domain. Okay, it turned out that this D repeats accelerate target DNA search kinetics, and we observed such effect for an artificial DNA binding proteins fusing antennapedia homeodomain and the D repeats, and we found the same thing. It turned out that actually the auto-inhibited state can undergo electrostatically driven induced fit, because the D repeats are highly negatively charged and the DNA is also negatively charged. So when the protein contact with DNA, the tail can be pushed away from DNA and it goes transitions into uninhibited state. Okay, I skipped this one. We got a kinetic model to explain the acceleration effect. Anyway, our method allows us to measure directly near-surface electrostatic potentials. And this method doesn't require any structural information. So this method is really useful for intrinsically disordered proteins. But I should say that this method is not the only experimental method that allows us to do research on electrostatics. As you know, there are several other methods like PK shift, NMR chemical shift, vibrational Stark effect spectroscopy, double resonance EPR, or redox reaction kinetics. But I should say that our methods give really much greater number of experimental data because many of these methods require labeling of biomolecules like EPR probe or redox reaction probe. And in the case of pKa measurement, you have to use just titratable groups, but our method works for any protons. So the data point you can get from our method is much greater. And our method is solution-based method. So compared to other methods, our phi-NS method has really major advantages for electrostatic research. Okay, quite recently, another group used our phi-NS method to study liquid-liquid phase separation, LLPS. And they basically demonstrated that in a liquid-liquid phase separated state, the electrostatic interactions are quite important, and that can be analyzed using our method. So we are quite excited to see this kind of application only 1 year after we published the method. Okay, so as you know, usually people regard NMR spectroscopy as a method to study biomolecular structures and dynamics. But I think we can now say that NMR is also really good at studying biomolecular electrostatics. Okay, so these are the people who worked on this project. Behind you and C1 did major part of research. And we got a lot of theoretical guidance from Monty Pettit's group. And we did collaboration with Jakob Levy's group on coarse-grained molecular dynamics. And these are the funding source. And finally, I thank you for your attention.
Thank you very much.
Walter, up here. Can I ask?
Okay, yes.
Okay, great, thanks. Very interesting talk. So let me just get this right. The nitroxide is in solution and it's scanning the whole surface. Okay, so there was once a time when people were very interested in nitroxide labeling for both NMR and EPR. So there are proteins where people use this to label certain residues to measure. I think something similar to this. NMR is not my field. Have you taken or maybe gone back and looked at some of those proteins and done this methodology to see how it compares to what's previously been investigated?
Okay, so basically for EPR methods, the original application came up in 1992, and the application was on the DNA and also membrane, double layer lipid, and we can test actually quite easily for the DNA, but their experimental values were not in good agreement with theoretical predictions. And one reason could be that when they introduced the EPR probe onto DNA, they used intercalation between DNA base pairs. And that may itself cause quite drastic structural change, and that may cause large discrepancy between the experimental data and theoretical prediction. Another possibility is that they didn't do really a good way to estimate theoretical values. It looks like they just used a simple approach, and they didn't use something like what we used here for the back calculation. As I mentioned earlier, there are two methods for our case for the back calculation. For that EPR work, they didn't do anything like that. They just used a simple I value at a particular grid point. That may be another source of discrepancy. We don't know that really the real factors that cause big discrepancy. But I should also mention that we did experiments for DNA as well. And in our case, the discrepancy was not too bad, actually. Here, this is the plot for the DNA FINS and theoretical back calculation. Actually, RMSD is, not RMSD, sorry. Correlation coefficient is slightly worse compared to the protein case, but it's not too bad, as you can see here. All right.
That's really interesting. So, first of all, I want to ask a clarification. Are you attaching the nitroxide to each residue, or are you just?
Oh, okay. So basically, the nitroxide is floating in solution. There is no covalent bond between the nitroxide and the protein. So that's why we call it co-solute. So basically, these small compounds and biomolecules are present in the solution, but there is no covalent linkage between them.
So if the nitroxide likes to be in one part of the protein and not as much on the other part,
right? That's right. So maybe this can clarify your question. So basically, these compounds are floating around the molecules, but it's not uniform distribution because of the electrostatic potential. And there are some bias in spatial distribution, and we use such bias to get the electrostatic potentials.
Okay, so so you had very modest potentials. They were about 20, 40 millivolts. Let's say if you lower the salt, do you see the?
Yes, that's a great question. And actually, we worked on it and we tested that method from 30 millimolar ionic strength up to 735 millimolar. And to our surprise, even at highest ionic strength, the agreement was not too bad in terms of RMSD. In terms of correlation coefficient, it was worse, but it was not too bad.
I guess you need to use nonlinear Poisson-Boltzmann, but all right, and I guess the last question, because I'm more interested in potentials inside. Is there some way that you might use something with a cavity where you could bind the nitroxide or a crevice where, so that you'd be seeing more internal potentials?
That's also a great question. Actually, because we have to use these co-solutes in solution, if those co-solutes cannot go into internal cavity, we cannot really use the method. That's the limitation of this method. Sorry? Yeah, so, okay, I should admit one thing. When we used this method for DNA, actually, some systematic difference was observed for adenine H2 site, and that is actually at the bottom of DNA minor group. As you know, minor group is quite narrow, and maybe the nitroxide cannot really go inside the minor group, and that may cause a large discrepancy. So there are some limitation arising from such accessibility of the probe. But when the co-solutes are accessible, yeah, this method gives a quite nice tool, way to evaluate electrostatics.
So I have two questions. So one, actually, to go back to the picture of the probe, could you make okay, so this is probing how far, a couple of angstroms from the surface?
Okay, so the range of ENS zone depends on geometry, but typically the radius of the ENS zone is 8 to 15 angstrom.
And could you make this larger by adding more carbons, so to look at like whatever the zeta potential?
That's another good question, great question. Actually, this method is currently using nitroxide probe, but if you use stronger paramagnetic materials like gadolinium ions, it can reach longer distance. So the ENS zone may become larger. And we are now working on improvement of the co-solute molecules because for example, this method cannot be used in the presence of reducing reagents like DTT or BME, but gadolinium chelates should work even in the presence of DTT or BME or ascorbic acid. So the use of gadolinium will expand the applicability of this method. That's what we are working on right now.
And so my second question is for the intrinsically disordered region. So, and also when you say like you had used 100 conformations, is this 100 conformations coming from molecular dynamics simulations?
Oh, that was actually just initial PDB structures together with randomized conformation, randomized side chain and loop regions in the presence of conformational databases. So probably sampling is not too bad, but it may not be realistic.
Okay, thank you. Very nice.
Thank you.
I have a question too. What happens for superficial tetrabond residues? Do you get the Boltzmann average of the potential? What would you get?
Please say again for the
case you have a tetrabond residue, so something that can change the protonation state. What is the potential that you measure?
Okay, so typically in our experiments, we use a neutral pH because at neutral pH, the charge of the probes become basically certain. In other words, +1 or -1 for on these. But charge state of the titratable groups doesn't matter at all for our method. Basically, but when we back calculate phi NS, of course, charge really matters, right? I mean, for which one? Yeah, this calculation. For that, we just used ProPKA and we used APBS with nonlinear Poisson-Boltzmann option for the back calculation. But I'm not sure if I'm really answering your question.
No, the point was, if you are measuring the local potential, what happens with if you have a site that can change during time, the potential because of the change charge.
Sorry, still I don't understand.
What happens in case you have I don't know a site that for 20% of chances of being neutral and 80% of chances to be charged?
In that case, the average, I mean, experimental value will reflect the average. But for example, for application of the, of this method to IDRs or IDPs, of course, there are many different conformational states. And what we get is just ensemble average. Same thing is true for the charge states.
Okay.
I would like to check some technical details. The first one is you mentioned the surface. So how do you define this surface? Like here.
Okay, so you are talking about how we define the range of the surface for the back calculation.
Yeah, because it's a near surface potential.
Okay, for that, as I mentioned, there are two ways for the back calculation. One is to use the entire grid space. And for that one, we don't have to set any criterion. So it's more objective. But we can actually use local space. And for that, we have to use a particular criterion. And our criterion for the definition of ENS zone is shown here. It's basically a region that gives a 68% contribution to overall of the sum of R2 minus 6. Okay. And that's the definition of, empirical threshold, I should say, for ENS zone. And when we define the ENS zone by this threshold, basically these two become quite close, as I showed here. Here. Okay, so green and blue are pretty much the same.
So this surface is like more close to what kind of theoretical surface we have? For example, molecular surface or van der Waals surface. Which surface? URE and the S surface. It's more close.
In this case, we just used a crystal structure and it's just X-ray crystal structure.
Okay.
It has some bound water, but we didn't really use the water coordinates. We just used protein part for the calculation.
Okay, I see. The next question is for the in your formula to getting this potential, you have this transverse magnetization, gamma 1, gamma 2, and then there's a potential term inside. Is that one you do the you obtain from the NMR experiment? You call the mean force.
Okay, so we get basically this ratio from NMR data, and that is completely independent of structural information. It's just purely from NMR data. But when we calculate from structure, I mean, when we calculate phi ENS from a structure, we use Poisson-Boltzmann potentials and the distance between the grid point and observed nucleus.
So the MR output is that term.
Just this one.
Okay.
Just this one.
Thank you.
Okay.
Like 68%. What will happen if you do 70?
Okay, so if you use larger ENS zone, basically the value becomes systematically smaller because at the more distant site, the potential is smaller. It's clear from this one, right? If you look at this two-dimensional plot, basically a site far from the protein surface has a smaller electrostatic potential. So if you expand ENS zone, basically you reduce the magnitude of the electrostatic potential. And 68% turned out to be a good threshold that gives a nice agreement between these two. But we don't know why it is 68% rather than 30%, 90%. This is just completely empirical threshold.
Okay, my question is again related with that ratio of gammas. Are those the so-called ion excess values that you get from the ion quantification experiments that you also do? Is that it? Those gammas, each of those gammas is an ion excess? Because in some of your papers you measure that by ion quantification, right?
Basically, in this case, we measure just proton signals. I mean, protein or DNA proton paramagneticization enhancement, and these quantities are not through the observation of ions or co-solid molecules. They are just from protein NMR or DNA NMR. Yeah.
Well, they are not related to the ion excess.
Okay, we also do a lot of ion NMR as well in our lab, and we use special equipment for that. And we measure, for example, sodium NMR or lithium NMR, cesium NMR. Yeah, we do a lot of ion NMR as well. But here, this, method is not related to ion NMR. This is simply biomolecular NMR.
Okay, thank you.
Okay. Thank you. One question. These probe small molecules, can they attract ions in the dissolved ions, and can that screen the effect of these?
We have never thought about that possibility, but considering that this is charged, there should be some electrostatic interactions with other ions present in the same solution. But in our back calculation or experimental analysis, we don't use such information at all. But still, we get quite nice agreement.
Okay, one more quick question. Make sure I understand. The phi ENS is associated with each residue on the surface.
Right.
Okay.
That's right.
And the 68% distance is from that residue.
Right, that's right. From the observed nucleus, hydrogen nucleus. Yes.
Okay. That's where the measurement is.
That's
gamma 2.
For the back calculation. Measurement doesn't require any distance information at all.
Right. But you're measuring the gamma 2 plus minus is measured for a particular place in the residue.
That's right. And we can measure such gamma 2 for many residues at the same time from a single experiment.
Thank you.
Hello? Oh, there it is. No, thanks a lot. Very interesting. I was just wondering about you have very good agreement with Poisson-Boltzmann calculations. I was wondering how difficult it was to get there. I mean, what parameters did you use, say, dielectric constants and
okay. Regarding dielectric constant, actually, when we published the first PNS paper on this method, a reviewer asked us what kind of values we used, and they also asked us to test some different values for the dielectric constant for the internal regions, and we tested from 2 to 20, if I remember correctly, maybe 2 to 10. But anyway, for this particular method, the dielectric constant for the interior region doesn't matter much, probably because these are about exterior electrostatic potentials. But if you need to get information about internal cavity, probably the dielectric constant for the interior region is very important, right? But not for this case.
Okay. Thanks a lot. Thanks again, our speaker.